Almost, sir. Shall we start?
Satish sir.
Good morning. Yes.
Sir, give me a minute. I'm having some power source problem here. Give me a minute.
Okay.
Okay, give me a minute. Give me a minute.
No, it's okay. Dear participants, good morning to all. We'll start the session within 5 minutes.
Okay, Satish sir.
Now, shall we start now?
Yes, sir. Yes, sir. Sorry for the interruption.
It's okay.
Okay, can go ahead. Can mute myself.
Dear participants, good morning to all. Welcome all the dear participants and the speaker for the session. For the 5 days, ATAL sponsored, ACT sponsored online FDP in the college, Rajashri College of Engineering, Bangalore. So now in the day 4, we have the speaker for the first session, Dr. Pramod Kumar SK, Associate Professor, is going to deliver lecture on Artificial Intelligence for Manufacturing. I want to introduce the speaker for the session, day 1, the day 4, session 1. Dr. Pramod Kumar SK is working as an Associate Professor in the Reva University, Bangalore. And he did PhD in universities in Malaysia on CAPP camp in 2018, and did MTech in Viswesvaraya Technological University on product design and manufacturing in the year 2011, and he did BE in the University Technological University India in mechanical engineering in 2007, and he has professional experience. And from September 2007 to 2008, October 2008, did as a graduate training in the Fluid Dynamics Private Limited, and is did from 2011 to 2013 as assistant professor PSIT Bangalore. So here I want to share my personal experience. Now we are worked as a colleagues presently at PS University. So I'm very happy to with us the Pramod Kumar SK as a friend as well as a speaker for the day 4 session 1. Welcome Pramod. And also he has worked as an associate professor. He is working till now from August 2008 to till date as an associate professor in the Reva University, Bangalore. And his research areas are applications of artificial intelligence for tool wear production during machining of difficult to cut materials and in-process tool condition monitoring, application of image processing method for integrated pest management in agriculture. And he has did several publications, published a lot of papers in SCI journals, 5 SCI journals are published, and he has published 3 book chapters, and he has published 11 Scopus Index journals, and he has published many papers in the national and international conferences. And he has published one patent, and he's also got one research from Asian India RTF in the year 2021 as a research grant. Presently, he is guiding one research candidate in Reva University. Thank you very much, sir. So personally, I invite Pramod Kumar SK in behalf of Rajarashri College of Engineering and ACT's ATAL Online FDP for this day 4 session 1. Welcome, Pramod. Over to you.
Thank you, sir. Thank you, Dr. Fashar. Very nice to meet you again, as you said. Okay. So I'll just share my screen. Okay. So very good morning to one and all, to all the professors who are participating here for this wonderful FDP. So I hope I am audible, clearly audible. So there is no problem in my. Okay. Okay, sir. So I'll start with my topic today, which is AI for manufacturing. Okay. So we all know currently the global technologies, various global technologies, there's a buzz around. So we talk about the smart product, we talk about the voice recognition, we talk about the virtual reality, and also we talk about AI, which everyone speaks now. And also there is one more, I call it as lidar technology. I think you might have, all of you might have come across that. So lidar technology is X-ray type, so which can be scanned from the sky to any dense forest, any landscape area, and we can find what is beneath that particular landscape. Okay, so these are all the global technologies which are being emerged and are into development and also being utilized at a certain extent. Okay, so let us concentrate on the artificial intelligence today. So what is this artificial intelligence and why it's required for us? Being mechanical, we didn't come across any tools, any software tools other than C programming, right? So I think almost all of you are only might be familiar with the C programming, if I'm not wrong. Okay, so how this AI can be implemented in the manufacturing? So already we have seen past 3 days, many expertise have been talking about the lean manufacturing, the smart manufacturing, the industry 4.0, okay, and also they do have mentioned that just in time, Kanban, they are well versed techniques. So where we can get a efficiency up to a large extent, but not we can reach to 100%. Okay, so when we have already the lean manufacturing into applications, we have just in time, we have Kanban. Okay, so why the world is looking for AI now? The question is why we are into AI now, why it's required, and why it's required especially for us, for mechanical industries. So that's the question now. Okay, so because since we are from all completely from the graduation, we are into mechanical, we are into someone studying into thermal stream, some are into manufacturing stream, some are into material stream, but we don't come across the AI technology anywhere, so we are not familiar with those topics. Okay, but on the other end, the software people, they are well versed with the data is well versed with the AI methods. Okay. So just I want to highlight here why those people cannot be recruited into mechanical companies for AI applications, for AI purpose. Okay. The reason is, even though they might be well expertise in the programming, but the problem is they don't have the basics of the mechanical. They don't have the basics of mechanical. So they cannot learn the 4 years plus 2 masters, 6 years plus maybe 5 years PhD. So they cannot learn the 11 years of knowledge in just 1 year or in just few months. Okay, so that's a drawback what they have. But in other case, we have a lot of mechanical knowledge, and to integrate with the AI, it's very easy. Okay, it's just maybe a year effort. Okay, so what AI includes already, I think most of you are known to that. Some talks about the Python programming, some talks about the C++. Okay, so these are all the supporting programs, what I can say, where we can build the algorithms in order to make it adaptable to our manufacturing stream. Okay, so that's it, just a few highlight about AI. So now already we know about the industry 1. Okay, so do researchers quote that the industry 1. Okay, the industry 1. So it was marked by a transition from manual production, okay, manual production to the steam power. So industry 4 highlights about the steam engines, wherein the trains engines came into existence, run by steam engines. Okay, that was all about industry 1. So next, that was not sufficient for us. Okay, because technology is a must. We have to grow up. So the world came up with the next concept, industry 2. Okay, so what this industry 2 looked into? The mass production. Machineries came into existence, high production came into existence, and there was significant growth in the economy. Okay, so this again, mass production, which was most considered as efficient technology, it was again overtook by the lean manufacturing, which has been expertise I've been discussing in past 3 days. Okay, so lean manufacturing, it's like a most efficient method than the mass production, wherein we can save a lot of inventory, we can zero down the inventories, we can zero down the defects. Okay, so that talks about the industry 3. So industry 3 talks about the technologies next to lean manufacturing, wherein we can use the CNC machines. So I think almost all of you know how the CNC machine works and how efficient they are compared to the conventional machines. So even now, all the industries, they are using the CNC machines. It has been into existence maybe past 5 decades. So CNC machines have been used, and so industry 3 I mention it as a manufacturing which refers to the subtractive as well as additive manufacturing. Okay, so some might quote that additive manufacturing is industry 4. I say it falls under 3 rather than industry 4. Okay, so why? Because I will come to that. Why industry 4? Why additive manufacturing doesn't fit there, or why it has to upgrade itself in order to fit into the industry 4. I will come to that in the next slide. Okay, so industry 3 also had a computer aided manufacturing. So we are all versed, we are all, I think, have the knowledge of what is the CAM, and also we are into the handling of subjects CAD CAM, right? So wherein CNC machines, NC program can be fed into, and it will ensure the components which are machined out are of perfect dimensions. Okay. So industry 3 even until 2010 was perfect, and is even perfect now. But again, the global is talking about industry 4 using of AI to the manufacturing. So one reason I would like to quote here is, for example, I consider the Bosch industry here. So Bosch industry, even they were having the CNC machines all these years, which were operated by the machine operators who are expert in handling the CNC machines, and the production was very good. But now they are also trying to change over to the non-traditional machining concept. Why? The reason is they have the workers conflict. So there is a union, even though it's a private company, private OEM. So there is a union, workers union. So very frequently they do oppose the company demands, the company regulations. So what happens due to that? Since they are the direct laborers there, they are the direct laborers. So it will affect the production. So the reason is that they are changing over to NDT now, because AI still it's like under construction. Okay, so AI still need to be implemented completely into the industries. So until then, now they are changing over to NDT. They are trying to use abrasive water jet machining. Okay, and also Bosch, they are also trying out AI methods in order to find, the problems that do occur during the machining process. Okay, so what will happen due to that? We can solve the problems before it happens. We can solve the cutting tool wear-out problem before it happens. We can solve the machine breakdown before it happens. We can solve any dimensional problems before it happens. So that's the advantage of using AI. Okay, so these are some of the reasons why the global is looking into Industry 4.0. So next slide, it talks about the Industry 4.0. Okay, so this, as I said, it came a decade back, 2011. The term existed, Industry 4.0, and it was first named by the German government. So Germany was the one who tagged the Industry 4.0, and already I think most of you are familiar with these terms, cyber physical system. Okay, cyber physical system, IoTs. So we are most listening to these words in the past 1 year or few months. So what is cyber physical system? Okay, so it's an interaction between the physical system as well as the cyber world. Okay, so they quote, when it comes to the manufacturing things, so they quote it as cyber physical production system. They quote it as cyber physical production system. So which relates to the manufacturing things. So again, Internet of Things, IoT. So it depends what stream we are referring to. When we are referring to manufacturing, so all the things which are come into the cyber physical contacts, so they are manufacturing things. Okay, so let us leave this CPS as well as IoT to the software people. Okay, there is not much mechanical thing into that. So it's a communication between the systems. Okay, so even we want to get well versed into CPS, so it's a, my point of view, it's a bit time consuming. Okay, so let us stick to the AI thing, the machine learning. Okay, so also I think you might have seen people highlighting, researchers highlighting smart manufacturing, Industry 4.0. So Industry 4.0 is nothing but termed as mass manufacturing by USA, smart factory by Korea. I think all of you can see the last content here.
Yeah,
Is it okay? Okay, for me the screen it's okay. Okay, so yes, even you can see the China 2025 made in China. They want to put it as 2025 made in China in 2025. So maybe another 4 years. So everything will talk about made in China. So you know what happens when we talk about made in China. So it will be made in China itself. Okay, so Japan and the Italy, they are termed Industry 4.0 as their own specific way. Okay, even if India, we grow up into this AI in competition with the Germany, US and other countries, so we can come up with a new term. Okay, So, but it all talks about again the one stream, the AI applications. Okay. So, just I mentioned the to avoid the tool wear before it happens, to avoid the machine breakdown before it happens, to avoid the noises or vibrations before it happens, which is possible only by AI methods. Okay, so I do term them as out of process control conditioning, which was faced in industry 3 and in process tool condition monitoring in industry 4. So this is what, if we are want to jump into the research topics now other than materials. So if you are in the core manufacturing, I suggest jump into this in process tool condition monitoring, which is nothing but the industry 4 which the grant people look into. These are the buzzwords when you talk about in process tool condition monitoring. Okay, so out of process tool condition monitoring. So what this actually, so this has been adopted in industry 3 or you can say industry 2.5. Okay. So wherein if the tool wear happens, so we have to stop the machine, get the tool out, get it studied and find the crater wear, find the flank wear, then may come up with the solution for that. So it's like during that study time the production is stopped, right? So that stoppage of production can be avoided by industry 4 what I call it as in process tool condition monitoring. In process tool condition monitoring. So what it actually does is, so the tool wear can be monitored during the machining processes. The tool wear can be monitored during the machining process before, I can say, the catastrophic failure of the cutting tool. And this catastrophic failure happens especially when we go for machining of superalloys. So nickel and super base aluminum are the superalloys. So I think all of you know where these materials are used, the spacecrafts. Okay. So these materials, they are very strong in properties. So I am not a material guy. So I think most of you know the properties of those superalloys. So they are very hard to, or I term it as difficult to cut materials. I term it as difficult to cut materials. Okay. So even if you go to the ISRO website, they do come up with problem statements every year, and you will find this problem statement in their research problems, whatever they highlight every year. Definitely you will find here. They will mention it as difficult to machine or machinability of the superalloys. So even they are working on it. Okay. So in process will not, I can say 100%, but will provide much more solution when we come up with the, or when we compare it with the out of process tool condition monitoring. Okay, so I will talk to this, I will in detail, I will come to this later. Okay, so this is what the differs between industry 3 and 4. Okay, so to jump over to the industry 4, as I said, using of AI is not so easy. Is not so easy because we need a ladder in between these two. Okay, right now the production, the industries are balancing on 3 and 2, or I can say 2.5 and 3. Now they're trying to jump over to the 4. Okay, so just to jump over suddenly to the 4, it's not easy. Okay, why I tell you? Industry 3 all talks about the same computer integrated manufacturing, wherein we have been using computers to run the machines to get efficient way of production. Okay, so as I said, industry 4. Industry 4 is whatever the problem that do exist in the automation can be solved by using algorithms. By using algorithms. So how do we build these algorithms? So can anyone in the participants, how do we can build these algorithms? What platform, what software, what tool we can use? What workbench we can use in order to build these algorithms?
Dear participants, you can unmute yourself and interact with the speakers.
Okay, anyway, I do mention in the second slide what AI refers to. So it refers to the Python. So you might have heard of this. So maybe in some of your institutes, they might be insisting on get well versed with the Python programming. So C++, we have been hearing about this past 2 decades. Okay, so these two are the workbenches where we can build an algorithm which solves the problem of the automation. And what problem? This is what it highlights. So we can predict the tool where of a particular cutting tool before it fails, before it breaks down. Okay, so Python, C++, it's a, I think it's a basket of arrays. It's a printers, scanners. It has loops. Okay, so all this includes come in C++. What happens? What the more enhancement in the Python is, it's a bit more flexible compared to C++. So we can compile it easily, means less errors. Even we miss some commas, we miss some brackets, that will be fine by the Python. It's more flexible for the users. That's what the Python. Even you can use C++, which comes in Visual Basic, to develop an algorithm. I will also say how to develop the algorithm with the flowcharts. Okay. So again, I think most of you are not familiar with the industry 5.0 now. Okay. So global, some of them, 70% of them are talking about 4 point. Remaining 30% are already into 5 point. Now this is a bit exhausting now. We are into 4 point. We are just a toddler there. Now we talk about industry 4 point. So what is this industry 5 point? So industry 4 point focuses on a value driven initiative. Industry 4 point is a technology driven AI based manufacturing. Industry 5 point is a value driven initiative. Okay, and 4 point focuses less on the original principles of sustainability, whereas this focuses more on sustainability. Okay, so here we have AI driven technologies in order to control, in order to make it more efficient than what we found in industry 3 point. And industry 4 point, it focuses less on AI driven efficiency, and what it more focuses on is this one. Alright, so in all the aspects we look into this. So when we talk about AI, so that means we are looking into the efficiency in terms of energy, in terms of efficiency, in terms of smart materials. Okay, that's very good. Okay, so now what are the side effects of that? Economy, the CO2 reductions, the human centricity, because when we bring AI, already we have removed most of the direct labors, because, or maybe we are already out of indirect labors because we have CNC machines. Okay, so when we compare the CNC with non-conventional, we need indirect labors more there, but when you talk about CNCs, we need less indirect labors. Now when we talk about industry 4 point, we even don't need direct labors, or their interaction with the machines is reduced. The percentage of interaction of the direct labors in a production is completely reduced when we compare it to the industry 3 point. Okay, so now what happens? So that means there is lot of job loss, especially in India. In India we are more populated, so we are less into the automations. Even if you see small scale industries, they have lathe machines. We have lot of people to work on that. Okay, so even whatever the quantity required, we can achieve that by conventional way. So what happens if even the industries of India talk about Industry 4.0? So this is what the Industry 4.0 will look into. Policies, the agilities, how far it's affecting the environment. Okay, this is very important, environment. So just to quote out of this, the fastest city which is sinking in the world, the fastest city that is sinking in the world now. So anyone aware of that? It's Jakarta, the Indonesia. So by 2050, part of North Jakarta, which is in Java Island, is going to be submerged. So they are changing the capital. You might have heard in the news recently, 2-3 days back. So they are changing the capital now. So it's maybe the 5th country to change their capital city in the world. Okay. So this, whatever we are into going to developing technologies, but on the other end, there is a climatic effect. This is what the Industry 4.0 look into. Okay. So just to show what already the world into Industry 4.0. Okay, so again we will come back to the Industry 3 and Industry 4. So how to connect this? Okay, so I just discussed Industry 3.0, Industry 4.0, out of process tool condition monitoring, in process tool condition monitoring. So how to bridge between these two? Okay, so just to recap again the Industry 3.0. Okay, so all of you are well known with the CAD, correct? All of you are well known with the CAM, computer aided design, computer aided manufacturing. Okay, so all of you are well versed in the softwares we use for the CAD. All of you are well versed with the CAM softwares. Okay, so NC programming we use for the CNC machines. And in previous, a day back in talk, someone questioned, I think, what are the software we use for 3D printing. So I just want to say that all 3D printing, whereas it can be textile, automated machines, it can be 3D printing machines, it can be laser cutting machines. So in order to guide the tool, the NC codes are used. Even in 3D printing, the NC codes are used to guide the tool. Okay. So little we heard about the CAPP. Already we jumped into Industry 4.0, but few people came across what the CAPP is. So it is computer aided process planning. So when we have computers integrated for design, which is the initial stage of the production, and we have CAM, which is the final stage of the production. So what about the intermittent? So process planning, after design we have to go for the process planning for the optimal design in order to make it to production. So how can we use computers here? So that the computer will does our job. It will do process planning for us. Okay. So I will call this CAPP as the bridge between Industry 3.0 to 4.0. I will call this CAPP as the bridge which connects the 3 and the 4. Okay, so just I think all of you can see the flowchart here, so there is no issues. Okay. So artificial intelligence, so what we are discussing about past 20 minutes and what it requires in order to predict the tool. So we need the material data. We need the machine tool data. Okay, what type of machine tool is being used, what are the cutting speed, what is the feed, what is the depth of cut. So it requires certain data. It's not a smart, it's just artificial intelligence. We have to make it smart. So someone might be, they say maybe around you, they were talking about how we can make the machine learn. How we can make the machine learn. We have to teach it. So we have to bring it to a stage where it can does the job for us. So how to do that? We have to input the data in order to train it the way what we want. Okay. So we can input the cutting parameters data. So for example, I was talking about the superalloys. So some of you might be familiar with the cutting speed required to cut the nickel superalloys or the titanium superalloys, and what type of cutting tool is required, whether it has to be coated, PVD coated, CVD coated. Okay, so that parameters has to be input here, and materials data has to be input in case we are concentrating on how the material affects, and features dimension data. So I want to focus more on this now. So features, so when I say about features, so features is about the shape the component is made of. Okay, so we know all the operations, drilling operations, pocketing, then slot cutting operations, and V slot, okay, threading operations, grooving operations. These are all the features. These are have been termed as features. Okay, so when we talk about artificial intelligence, okay, so we have given a particular component to this AI method to machine out, and to machine out that particular component, it has certain features in it. It may have holes in it, it may have through holes, blind holes, it may have pocket, it may have grooves, it may have threads, it may be a cylindrical component, it may be a non-cylindrical component, okay, or it may be a irregular shaped component. For example, the turbine blades, the impellers, okay, so which are very difficult to machine out or very difficult to get the shape. Okay, so those shape data has to be input here, so which is done by the CAPP. Okay, so this is a vast subject, CAPP. Even we can do a PhD on this. Okay, so when we have all this data, we can go for the two-way prediction, because when we talk about AI, it's automation, completely automated, or 5% human intervention. Okay, so I term this CAPP as a bridge between 3 and 4, so it's 3.5. Okay, so what the manufacturing is all about, as I think we are already familiar with these stages: idea generation, CAD model, then CAM, machine out using CNC machines, we get the product. So what lies between these is the CAPP. What lies between these is the CAPP. So what this CAPP, so this CAPP is built on these techniques: feature based, knowledge based, neural networks, almost all of you are familiar with this stuff, genetic algorithms, fuzzy logic, pertinax, agent based. Okay, there are again volume decomposition method. Okay, volume decomposition method is called, and these are most efficient approaches. Okay, so wherein we can make the computer to do the process planning for us. Okay, so in order to do the process planning, it has to identify all the features. So as I said, all the features means it has a cavity, it has a protrusion, it has a boss, it has a slot in it. So those have to be identified by the CAPP. So how will it identify? It's not a human being. So we have to make it identify. We can depend on these techniques. So once this is automized, so this will be further more efficient automized. Okay, so I'll just take few case studies of this CAPP, which is based on certain algorithms. So before I go this, I would just show you, exit from the slide. Okay, I hope all of you can see this Word file. It's shared on your screen.
No, Brahma.
Okay.
For that, you have to share the screen. Now you are shared
Okay,
the
okay,
PPT.
okay. Maybe I'll just exit and share the screen. I will stop the sharing and I will try to share the screen, hopefully. Give me a minute. share screen. Okay, I think now it's shared on your screens.
Yeah, visible, sir.
Okay, thank you. Thank you. Okay, so classification. So as I said, features, it talks about the fillet, the step, the chamfer, the pockets. Okay, so you can classify on your own. You can come up with a new way of classifying that. Only thing you should have to be validate that. Okay, so I do have classified. I call them as regular form features. Why I call them regular form features? If you take a rectangular block, it is made of planar surfaces. It's made of planar surfaces. So that's why I call it as a regular form part model. So regular form, what it includes, I say it as volumetric features, surface based features. Okay. So what are these volumetric based features? I'll just go back to the PPT. I think all of you can see here, this is the V block part model. This is V block part model.
Your
Okay.
PPT is not visible.
Okay, okay. I will get back that later. Okay. Sorry. Okay. So let me finish out this. Let me discuss this regular form features. Okay. So volumetric means which has a mass in it. Okay. So whatever the components we use. So maybe we have the cell phones. Okay. Or when we talk about the gears, okay, so which we are most familiar with, the gear components, they are all solid models. So we call them volumetric features. And surface based features, the one which have thickness less than 3 mm, maybe our cell phone covers, they are surface based models. Okay, or when we talk about the automotive components, the BIW, body in white, or the car models, okay, the surface based models. So when we go for the design using SolidWorks, so we can create a surface based model which can be used for meshing, which can be used for analysis, and we can create a solid model, okay, which has a mass in it. So we can further subclassify them based on the type of faces, based on the edges they have. So notch, slot we are familiar, shell features we are familiar, and V slots, U slots, again they may be running through the component, or they may be not running through the component, which I call it as blind. And coming to the drilled holes, again they can be running through the component, which we call it as through holes, blind holes, and non-circular holes. This is pocket. Non-circular holes, the other term has a pocket. So again they can be running through the component, which we call it as through pockets, blind pockets. Okay. So this is about the regular form, where the components have planar surfaces. It's completely made of plane shaped component surfaces. What about irregular surfaces? As I mentioned, the impellers, they have blades which have spline based surfaces. Okay, so very difficult to identify them. So how to identify them? So there we come across the terms what we call topology. Okay, so topology includes, we talk about the surface, the edges in it, the vertex points in it. So we can use those topologies and build an algorithm on that. So volumetric features, again in terms of free form, so we can call them as free form slot, free form hole, free form boss. Okay, again surface based features, B, bump, ridge, dart. Okay, so we can first classify them, how we are going to identify them later, and just I will again go back to the PPTs. Okay, so I just classify them as regular free form. Okay, so coming back to the V block, Okay, so I've taken one example here. V block, I think most of you are familiar, we use in the metrology labs. So I have just a bit changed these features with a slots here. Okay, these slots run through the component. So I call them through slots. So this is a U-shaped slot. This is a combination of U and V here. Okay, and this is again a U slot. This is a UV slot. So I have to term them as my classification. Okay. So these are the features it has, and it has some 4 drilled holes here. Okay. So how to identify them by the algorithm, not us. We know, we have the knowledge, we can identify them by looking at it. So how to make the algorithm to understand it? Okay, and this is the finished part, right? So how to get this finished part? We need a stock model. So we need a stock model of minimal dimension to get this V block. Okay, so we can regenerate that stock model in this way. If you see, we are going in the reverse way, taking the V block model, CAD model, building the material, taking it back to the stock model. And you can also see this in Autodesk Fusion 360. They have this feature. Okay, so you input some CAD model, just go there option, it's mentioned stock model. So if you click on the stock model, it will give you what size of stock model is required for a component. That feature is there in the Autodesk Fusion 360. Okay, we don't find this in SolidWorks or Solid Edge. Okay, so that is upgradation what the Autodesk has done for their 3D model softwares. Okay, so it's like a reverse engineering thing. Bring it back to the stock model and identify the size of these features. Okay, so how much material has to be removed to get this V block? This amount of material which runs throughout the component, and how much material has to be removed to get these 4 holes. So this is what the material. So these algorithms give the specific amount of material that has to be removed in order to get the V block. So we are using the CAD model, going back to its stock model stage and identify or get all the data that has to be performed in the manufacturing. This is what the CAPP can do, so that we can avoid whatever the mistakes that happen during the real-time manufacturing. Okay, so I call this as exported view. Even you might have seen when you open the SolidWorks, every component, even a crane is exported there. All the features you can see zoomed up. Okay, so even by using these softwares, we can algorithms, we can explore them. Okay, this is what I have shown here, the stock size of this V block, and we can color them. We can color as per our requirements. Okay, so which can make it a standard during the manufacturing. And what these green, the red colors, okay, the magenta colors, what these talk about, these are the material that has to be removed during the manufacturing to get this V block. So this is what we can achieve from the CAPP by building the neural network algorithms, agent based algorithms, volume based algorithms. And we can even identify these features. So it also gives us the data here. This is what we can get from the algorithm, the output, the table. So how many circulars are there? 4 circular holes. So how many slots? 4 slots. So what are its material volume that has to be removed during the machining? So this is the amount of material has to be removed. And what material? So you can see here, the blue color. If you remove this, we will get 1 through slot. And if we remove these green materials, we will get the circular holes. So this information we can obtain by the CAPP before we go on to the CAPP. And also we can get the complete stock model data. Okay, so what is the total material that has to be removed in, this is called roughing. Okay, sub delta volume for roughing process, sub delta volume for finishing process. Okay, I just term them as per their processes. So this gray color includes the roughing process, and green color, this includes the finishing process. Okay. Okay, so this is about V block, what we can achieve using the CAD model by CAPP. Next, what happens if we have more complex regular model? So this is a bit complex regular model. So what our algorithm can do, it can identify the features or not. So when we input this to the algorithm which has been statically built, so here it's a reverse engineering. We can get all the material that has to be removed, or if I say that is removed. Okay, this is the layer of finishing layer. This is the finishing layer, and one more way of identifying the features by these combinations. Okay, so chamfered, this CF means chamfered face, and B means boss face. Okay, and P means peripheral face. This is chamfer face. Okay, so I will just tell you one example here. So let us look into this through circular hole. Okay, so how this makes? Okay, so here is the combination. So by algorithm, we can designate the surfaces or faces of the feature. So we have a component, we have a drilled hole. So drilled hole has some surfaces in it. So we can identify the shape of those surfaces and designate them. Okay. So planar face, then planar face, filleted face, planar face, filleted face. So what this combination makes, it makes a pocket. So when we come to a drilled hole, circular faces, circular faces. So you can see a drilled hole means it's circular in shape. Okay, so that means it has circular faces in it or surfaces in it. So we can designate them. So these two combinations will give us what actually feature is. Okay, again the algorithm look into this, it designates them, it comes up with the feature name. This is another way of identifying the features, generating the material for that. Okay, so if you see, this is what material that has to be removed in order to get the original component. So again, this is the exploded view. So as I said, you can see the number of layers that has to be removed out, or the material which are colored materials that has to be removed out to get the particular shape. And also this quantity of the materials data is also can be achieved by these algorithms. Okay, so what about free form? So some of you might be thinking, what about if we use the impellers, if we use the car model? Okay, so these algorithms are built for volumetric features, volumetric part models, okay, which have mass in it. Okay, we cannot use that for surface based features. Okay, so if you have to use, we can use that, but again we have to look about the APIs. Okay, so application programming interface functions. So we use APIs here. So it's a open source libraries we can get. So based on APIs, we can go into surface based part models. Okay, so free form, again we can identify them, identify these features, then do the reverse engineering, build the materials. Okay, and you can see the missing material can be re-achieved by the algorithms. So how to identify, because these are irregular shaped, we cannot name them. Next time this shape may be another way. So based on colors we can identify them. So wherever there is planar face, we can quote a color. Wherever there is spline based, we can color it again in another way. Where is cylindrical, we can color it another way. So these colors can be made standard and we can identify based on these colors. Okay, so again we can achieve the type of feature from these algorithms, what is the volume into it required in order to get this component. Again, exploded view of this will give us an idea what are the number of processes we have to do, to achieve this shape. Okay. So these are the three case studies of different shapes of part models. Okay. So which can be built upon by using the algorithms. So I just highlight how to build these algorithms. Okay. So as I said, I did this on C++ platform, Visual Basic. Okay. So I will just highlight about the flow charts which is used to build all this or to study these three cases. Okay. Okay. So even we can get the chart of this, all the various color materials. So which is the major material that has to be removed, and we have some equations to be used there. So level of complexity can be found. So that means whether the component is complex or not. Whether it's simple, it can be machined out easily. Complexity, impellers, it's a complex component. Okay, so level of complexity. We can rate them up to 0 to 1. So 0.89, 0.7, 9, based on the shape. Okay. So I'll just again go back to share the flow chart here. I cannot include in the PPT, it's a very big flow chart. So kindly permit me, I will just unshare this and share again. Okay. Okay, I think the Word file is shared on your screens.
No. No,
No.
brother.
Okay. Let me try again. It's okay. Let me try again. I hope now it's shared.
It's shared.
Okay. So this is just one algorithm flowchart, okay, which I want to enlighten you all upon. So, okay. So when start, so what the first input has to be our CAD model. So to the algorithm, our CAD model has to be input. Okay. So whether it's a regular part model or freeform part model, okay. So that has to be input. Now I talked about the topologies. So I think some of you might familiar with the term topology. So topology, when I talk about the topology of a part model, it includes or it talks about the body of the part model, the surfaces in it, the faces in the surfaces, the edges in the faces, the vertex points in the edges, or the vertex points that makes two edges. Okay. So we have to extract them. So the algorithm, these algorithms are all based on the topology. They study the topology, they work on the topologies, come up with this solution. Okay, so this is what we can do a lot using the topologies. Okay, so identify the type of face, whether it's a regular face, planar face, or a free form face, or a spline based face. Okay, that has to be identified, or it's a cylindrical face. So loops, a face is made of, for example, a planar face is made of 4 edges, and these 4 edges combination is called a loop. Okay, these 4 edges combination is called a loop here. So identify those loops. Okay, so that loop again changes, the shape of that loop changes based on the linear edge or a non-linear edge. Okay, so identify those loops, then identify the faces. Okay, so if it is a planar face, we have then next we move on to build the material for that. It's a reverse engineering. So we are going to build a material for that. So we are using loft functions here. Okay, APIs I mentioned. So it's application programming interfaces. There are APIs, open libraries, even Dassault systems have those APIs. So wherein we can use for our mechanical purpose. We can use them for mechanical purpose. Because C++ we can just write a program, just say hello. You might have, when we study first the programming, the first simple exercise is say hello, right? So printfs, write, okay. But when we talk about the mechanical, we need the APIs in order to get the topology of a part model. Okay, so we have loft functions there. Loft is nothing but the offset functions. Okay, so we copy those surfaces or faces, make it two copies, keep a distance offset between them, then we can generate material between them using those algorithms. Okay, so we can generate the material between them. Okay, then if it is a feature, okay, so whether it's a hollow feature, that has to be identified. So again, based on the loops, based on the number of loops, based on the edges, it's identified. Okay, then identify the feature. Then again, once we generate the material for finishing, we generate the material for roughing surface. Okay, then based on the loops we identify them. Then there is the output, as I mentioned, a table is popped up as the output where it mentions the type of feature. Okay, so here I do have two approaches, two techniques here. One is rule based method, one is volume decomposition method. Because I am into reverse engineering here, I am regenerating material for that particular part model, take it to the stock model. Okay, so this is one simple algorithm, so based on which we can develop the CAPPs. Okay, I'll just stop sharing this, go back to the PPTs. Okay. Okay, so this is about what CAPP. So when we can automate the process planning, we can further automate the manufacturing. We can further automate the manufacturing. So what happens? We are into AI applications, which is completely automatic or very less human interaction there, but purely we are completely based on human interactions. We need knowledgeable person to do the process planning, we need knowledgeable person to do the list out all the processes. Okay, it's again like a conventional to non-conventional. It's a manufacturing made of conventional and non-conventional. So how to avoid that? We have to bridge this gap by CAPP. Okay. Okay, I think we will have 5 minutes just break.
Yeah, we'll have 5 minutes bio break.
And then we will come back. Okay.
Yeah. Thank you.
Thank you.
Hello.
Yes,
Hello,
sir.
Pramod, we will start the session.
Okay.
Now, the session will
Okay.
resume
Okay.
with 5 minutes by break. Thank you. Over to Pramod,
Okay.
sir.
Okay, sir. Thank you. Okay, welcome back, participants. We just had a 5 minutes relaxation. Okay, so just move on to the next slide. So I want some interaction. So whatever we have been talking about, the CAPPs, whatever the industry point, was the bridge required to connect to industry 4 point. So I hope all of you got some idea on that. So if you have any understanding, if you have any questions, any sort of questions to be asked, you can just let me know. Maybe 1 minute we can give a thought on that. Or you are not able to understand what actually it is. So I assume that all of you are quite able to understand what we were discussing, we were interacting this 1 year, sorry, this 1 hour.
Pramod, sir,
Yes, sir.
there is a question in the chat box.
Okay, okay.
What is the maximum level of complexity?
Okay. So this complexity I have rated to 0 to 1. 0 to 1. So if you see this, the concept car, okay, the car model which is completely surface based as well as a spline based. So it has lot major complexity. So if you see its rate, it's near to 1.79. Okay. So between 0 to 1, all the complexities will lie under. So maybe the turbine blades or the jet engine shapes, they come near to the 1. Okay. So this complexity level is again obtained by the algorithms which have been built. So this complexity it takes based on the shape it goes through, and based on the spline based surfaces it reads through. So it gives us a complexity level. So this is about to get the idea for the manufacturing team to know that okay, this is a complex component, so we need what type of machine. So if you see the 5 axis machine, 3 axis machine, 4 axis machine, so an idea is given to the manufacturing team. Okay. Okay, so we will move on to the next slide. So okay, so now artificial intelligence, industry 4 point, what we have been talking about. So I think most of you maybe you have some confusion over whether we say it machine learning or we say it artificial intelligence. So I say it's same as what we say sim and CAM. So we have a subject named CAD CAM sim. So I say sim is a general term, computer integrated manufacturing. Within that lies the CAD and CAM. But we do mention as a syllabus for the semesters CAD CAM sim. I don't see there is any interaction between that. Sim, I say it as a general term. Within that lies the CAD and CAM. And in between these two, CAD and CAM is the one what we are discussing about CAPP. Okay, same goes here. Artificial intelligence. So we talk about intelligence to make the machine intelligent. So how to make it? We have to make it learn. So how to make it learn? There are two things: unsupervised, supervised learning. Okay. So for us, we are like new into this world. We mechanical guys are very new into this world. These are like new terms. What we hear all these a decade. So unsupervised learning refers to clustering techniques component analysis technique, and hierarchical clustering. Okay, so this is, we are not into that, so we will leave to that. So I am not well versed into that. So we need to make a machine learn. So to make it learn, we have to focus on supervised learnings. So what this supervised learning includes, it talks about all the random forest, all the neural networks. Again, within that neural network, it has artificial neural network and feed forward back propagation, support vector regression, support vector machines. These are all the various techniques, I call them, so for the supervised learning. So what these can do, okay, so I just quoted here, supervised learning.
Pramod,
Yes.
PPT is not changing, I think so. Now we are seeing CNC milling machine selection.
Oh, sorry. Let me check. I'll just reshare it again. I hope now the
Yeah.
slide is on to artificial intelligence, right?
Yes, yes.
Okay. Okay. Sorry for all the participants. Okay. Okay. Supervised learning. We will more focus onto this. Okay. So why we need supervised learning? So why we not talk about unsupervised learning? Okay. So that's why I quoted here. Supervised learning, which means the training of a machine to enable it to choose a function, describing relation between the input and outputs, okay. So by this supervised learning we can get the outcomes, okay. Outcomes for what we have input. So here inputs refers to the machining parameters. I said about machinability in my previous slides. So machinability of supervised, which is very difficult. Some of you might researching into that. Okay, so it's very difficult to do that. So because the cutting tool has a catastrophic failure, we cannot say it fails at this particular cutting speed, which can be done in case of other materials. Okay, so that catastrophic failure is the major cause. Okay, so we cannot say this at this cutting speed the cutting tool will fail for supervised. Okay, so we have to input certain cutting parameters there. So just I will say 0 to 100 cutting speeds, which is suitable for machining of supervised. So what output we have to get is, what is the optimal cutting speed that is achieved before the catastrophic failure, or which avoids the catastrophic failure of the cutting tool. Okay, so we have to input data here to the algorithms. We have to input data, then they will start learning. They have the library in them with all the data we have input. Then once the real machining starts, they will just match them. Matchmaking. Machine learning is matchmaking. Okay. So that's why we need supervised learning. Okay. So just I am quoting one paper here, which refers to tool wear prediction in drilling of superalloys, and it's an in-process tool condition monitoring. I think already I have discussed what is in-process, out-process I have discussed. So when we talk about using machine learning for the tool wear prediction, so it's in-process tool condition monitoring. So how the setup actually can be. So this is one. So for Corney, who did in 2016, see already they are into this past 1 decade. Okay, so this is the drilling machine, the conventional drilling machine. Okay, so to get or to predict the tool wear here, to predict the tool wear. Okay, so what setup? So he is using a digital microscope here, digital microscope, to get the images of the drill bit, to get the drill bit images as it drills the given workpiece. Okay, as this is 625, I think the aluminum, so the material is used. Okay, in kernel 625, I think he worked on that. So during the drilling process, it takes the images of the cutting edges of this drill bit, input that becomes the data now, inputs those data to the neural network training, and also he has a dynamometer fixed to this workbench, and this dynamometer give us the cutting force data. Okay, so using these two data is trying to predict the tool wear before it breaks down, before the catastrophic failure happens to this drill bit. Okay, so how actually this neural network works here? Okay, so we have the images of the cutting edge, okay, as it start the drilling process, and this image will be fed to the neural network trainings. Okay, so this is the second time these images are fed to the neural network for the second time. Okay, earlier there's a library created in the neural networks, and that library has already the images of the cutting edges which has been wear out stage by stage. Okay, so now during the process, the image is again captured by the digital microscope, are input to the neural networks, and this neural network will perform the classification. I'm just saying one example classification and regression on these data. So it will match with the library. It goes to the library, take a particular image data, matches with this data, with the current data which is obtained by the microscope, digital microscope, then give us the wear prediction, give us the what type of wear is happening. Okay, if the flank wear or the crater wear, okay, so if the wear is more, that means this neural network will alarm us that the tool will attain this failure soon. Okay, so this is during process, so what happens, the advantage is we can change the cutting parameters to avoid or to further increase the tool life of the drill bit. Okay, so that means before something happens, we are going to avoid that, we are going to avoid the failures, okay, which cannot be done in industry 3.0. Okay, so now I said the images here, so some of you might be thinking how it matches the images, on what basis. So I'm not expertise in image processing, I have certain knowledge in that. So images, okay, so we call it as RGB. Okay, so I think all of you know what RGB means, the basic colors. Okay, so the RGB image is taken, so based on certain, there are equations, so we can convert it to gray image. There is called intensity factor. Okay, so those intensity factors we can change based on equations, and we can achieve the gray image of this, whatever the image from obtained from the digital microscope. And then from this gray image we can get certain properties. One I call it as entropy. So each image will have different entropy values. There are many properties. Okay, I'm just coding it here, the entropy, or I can say the contrast value. Okay, so it concentrates on these factors. So what is the entropy of a particular image where the tool wear just begin? So that value is different compared to the image which has captured at the last moment or when the maximum wear is obtained. So that entropy value is different. So it matches with these entropy values from the library and the image is taken during the process. So based on that, this is one example I am saying. There are even noise, vibrations data can be taken. Okay. So I am talking about wear data. So based on these property values, it can predict what type of wear or at what level the wear is being happening. Okay. So what are the outcomes? What he could able to achieve? Even we cannot say this is most optimal method. Even we cannot say this is most optimal method. So he had some drawbacks. What the drawbacks were? See, the error was obtained 0.8 to 18%, and for how many samples? 36 samples. For 36 images, there was an error of 8 to 0.8 to 18%. This is a bit huge. If you reduce the samples, the error was reduced. The error is reduced when the samples is reduced, which is not correct. Okay. So we should have more samples. Now it's 36. If we go for 100 samples, the value has to come down. The error has to come down. Okay, so that means what I am trying to say is still there is a lot of problem solving. Still there is lot of problem solving. Even this person he has done in 2016, but even today there is a lot of problems that are to be solved in this AI applications. This is just one application I am saying with respect to drilling. So it goes to turning, it goes to milling process, all the manufacturing process. Even so, most of you might be into materials. So how to apply AI for the materials? Okay. So I think maybe all of you are familiar with the ANOVA, right? So can I know why we use ANOVA there? Anyone? Anyone from the participants? Why we use ANOVA?
Yeah, dear participants, please interact with the speaker.
Yes, can you repeat? Not hearing.
It's not audible. Please give it louder. Any questions from the participants?
Okay, so ANOVA, I think, so we use to get the, suppose we have 200 data obtained from the machining process, so we come up with the optimal values. Okay, so we use ANOVA there. So we can use this AI method in order to sort out 200 sample values in material, okay, in whatever the sum results we get. So we can use AI there to get the optimal property values. Okay. So we can use this AI in all aspects, not only in manufacturing, we can use in all the streams. Okay. So this is about the one I quoted, the corner et al. So they do come up with the AI method, but again there is error still existing which needs to be solved. Okay. So I just previous slide I mentioned here there are random forest, artificial neural network, support vector regression. So when I gone through more papers on this, so I could able to say random forest is the most efficient when we compare it to neural network, support vector regression, okay, support vector machining. So random forest is bit more efficient because if you see here, the greater the samples, the greater the errors. So we can go for random forest as bit more efficient algorithm. So what it includes again, you might have heard classification they say. All CS people when they talk about AIs, they say about classification. Okay, so we know classification means when we talk about classification, we know the types. So classification and regression. Classification and regression. So these two are the steps in random forest. So what classification, what it does actually. So all of you have the mail IDs, we have Gmail accounts. And if you look, once you open the Gmail account, what we see on the left hand side? We see the primary inbox, we see the outbox, we see the spam, right? We see the important, we see the trash. So what does it mean? Any mail which is a spam, it goes to the spam box. Any mail which is relevant goes to the primary. Any mail which is important goes to the important box. Any mail which is not sent out, it goes to the draft. Right. So this is what the classification does here. So we have all the flank weight data, we have all the cutting force data. So it's just we are dumping all these data into the algorithm. So it has to classify. So it will classify them. Flank weight data, cutting force data, other data which we input. Right. So once we classify is done, next is the regression. So regression, what it does, there is some filtration in that. There are maybe some unwanted data which are not the perfect data. Those are removed out, okay, before a library is created. And then trees, okay, we know the tree branches, sub branches, okay, main branches. So this is what it does, it creates a family there. It creates a family in the library. Keep it ready. So whenever again we input the data, it will match them, give us the output. And the output what we are looking here is toolware. Okay, so this is just a concept and just overview on how we can use the random forest for our toolware predictions, okay, during the machining process, Okay, so now, so as I had mentioned that the AI was introduced a decade back, right? So in 2011, the Germans could able to introduce that. Now it has been 10 years. So someone might be thinking, so how extent the research has been achieved, okay? So I have a paper, okay, I referred a paper which indicates, just published a year back. Now we are in 2022, okay. So 2020 it was published. So they do indicate from 1957. If you see, people, some expertise have been looking into this from 1957, but not maybe mechanical related. Okay, software people already they were looking into it. So from 1957 to 2020. So if you see, these indicate the number of publications, hardly in single digits. From 1957 until I reach 2016. Right, it has been into existence, but maybe we are the last persons to come across it, because it has been already in 2016 double digit paper were published on it, and again still it's going down, coming up. I think if I say it's like a COVID graph, number of infections, okay. So now 2020, if you see again, hardly 6 papers have been published. This is globally I am saying, all top rated journals. So this I am relating to the mechanical, When I talk about 2016 to 2020, the AI application with respect to manufacturing, with respect to mechanical things. Okay. So what I would like to say here is, there is lot of problem solving in this. There is lot of problem solving in this field. So as I said, these are the buzzwords. Okay. So when we talk about industry 4 when we write a proposal on that, so it's like attractive thing for the reviewers. Okay, so I'd like to highlight one more point here. Okay, so coming back to this our complete manufacturing model. So I think now we have an overview. So idea generation CAD, it's almost achieved. Okay, I like to highlight one point in this CAD. So anyone heard about CMM? It refers to the metrologies. So can anyone derive what is CMM?
Coordinate based recognition.
Yes, thank you, sir. That's correct. So coordinate measuring machines. Okay. So we have a pointed machines. So wherein the pointed tool will come, which can measure any complex machine. So we can measure the dimensions there. Okay. So it's a way means the machine has to come in contact with the model to do that. Okay. So these are tried to be replaced by 3D scanners now. So all of you are familiar. So these are being replaced by 3D scanners. They are not up to the mark. Okay, it's being used. Okay, very few industries are using these 3D scanners. So wherein you use a portable gun type, so just run over the component, you will get the model in the system. I will tell you what the drawback is. So whatever component we get onto the screen by using 3D scanners, it's a non-volumetric. It's a non-volumetric. It doesn't show the volume into that. It won't be a solid model. It will be a surface-based model. It will be a surface-based model. So that means we can get the outer shape of the scanned model, but it's quite difficult when we talk about the internal features of that model. Okay. So idea generation is up with us. So 3D scanners are into existence now, and when we use CAPP 3D scanners, this is completely automated. This is completely automated. When this becomes optimal, these methods become optimal. So use a portable gun, scan the component, a model is created automatically, and the process is created automatically. Stock model is created automatically, all the feature data is created automatically, the amount of material removed is data is created automatically. So what is left? Go to the CNCs. And in CNCs, we have this waiting for the manufacturing to happen and to make it more efficient what we have now, more efficient than what we are achieving in the current industries. Okay, so this is very good what we say. Maybe in another decade we are going to achieve a lot, but again there will be industry 4.5 which will be again looking into the other aspects, the drawbacks or the side effects of industry 4. Okay. Okay. So coming back to this AI methods, even you can use these AI methods. So you can currently work on this. You can use for all your research areas, and so I just want to end up saying that now we are talking about industry 4, industry 5. Okay. Soon there will be industry 4 plus, industry 4.5, Industry 6 point, Industry 7 point. So they are not too distant far, but they may dawn upon us soon. Okay. So with this, I am open to questions. I hope I could able to highlight some of the current scenarios.
ये गैदरिंग है भाई साहब, गैदरिंग नहीं हो। वैसे लिखा नहीं व्हाट्सएप पे। सर जी ये सारे जो
It's not properly audible, sir.
बैठा तो बोलो ना, यूट्यूब बैठा रखा है कैसे।
Hello.
क्लिक कर रहा हूँ, दे रहा है मेरे बदले को कैसे आप
Audience, any questions?
काम नहीं लगा, दोनों क्लिक सही किए हैं ना भाई साहब। नहीं चले ना ये ऐसे। अभी इतनी देर बाद अगर आया तो सॉफ्टवेयर का काम पे।
Dear participants, any questions for the speaker?
Hello, sir. Good morning.
Good morning.
Good morning, sir.
Hello.
Yes, sir, you are audible. Yes, you are audible.
Okay, sir. Firstly, I would like to appreciate for the wonderful presentation, sir.
Yeah, thank you, sir. Thank you.
Secondly, I want to know about example I'm doing the machining. I've never used the DAC card. So how to use the DAC card and the LabVIEW software, and how we can relate it with the artificial neural network that you shown in your one of your schematic diagram.
You are. Can I know the terms you used? Data card, or you said some?
Yes, sir. Data card. DAC card that you mentioned in your one of your diagrams, DAQ. Data acquisition जो card होता है.
Okay, okay, okay. See, data in terms of maybe you are saying the cutting parameters data.
Yes, sir. Yes.
Okay, so it has to be connected to the algorithm. So whatever data you are extracting, you can directly input it to the algorithms. You can directly input it to the algorithms with the system. Okay.
Okay, sir.
But you should create a library in the algorithm. So you have to build the algorithm maybe using Python. You have to create, you have to build.
LabVIEW.
Yes.
Okay, okay, sir.
So you have to use a Python platform or a C++ platform to build algorithm. So first you have to input all the data which are you are experimenting on. So that becomes the library input, the basic data. So next when you come into the actual experimentation, those data will be continuously during the process can be input to the algorithm. So the algorithm will come up with the predictions what you are expecting.
Okay, sir. Okay, sir. Thank you.
Okay, so hope I have answered your question.
Yes, sir. Fine, sir. Thank you.
Okay. So any other questions, participants? Maybe we can just interact. So
Any questions
even
from the participants?
I'm not well versed into that. So it's all we are like a toddlers here.
Any participants? Any questions? Any questions from the participants? Now, I would like to ask personally a question for Pramod.
Yeah, yes, sir. Yes, sir.
Now, just to share experience, the research in University of Science Malaysia, how you are feeling, how you felt. I'm very glad to know that just you have left PS to do research in pursuing PhD work in University of Science Malaysia.
That's good. That's good. I just want to just highlight few of that. So I want to first start with. I think many of you participants maybe they are looking for maybe PhD studies in future. So there are two aspects. One is you can get into the IITs because now everywhere talk also about graduation from IITs or NITs. Or what happens if we go abroad? Okay. So the thing is, even I studied in USM, which is University Science Malaysia. It's a public institute, government institute. So if you see, its global ranking is 147 now. So when I joined, mechanical was 100th ranking in the world. Now the whole university is 155, sorry 145, which matches with all the IITs. Okay. So what I am got exposed to the new topics. Okay, so here in IITs you can find the same areas, lot of professors working on it, but outside environment is bit cool enough when we compare with our IIT institutes. IIT institutes professors are very well expertise, but we have to work to their expectations. USM or outside any institutes, top institutes, there will be experts and we have to be expertise to match them, but there is a little bit of relaxed environment outside, okay, which I could able to enjoy it in my full-time PhD tenure. And what I was expertised into CAPP, I didn't know what the C means, so once I go there I could able to study, develop algorithms. So I kind find the similar areas in IIT Bombay, okay, or IIT Chennai. So very few people are working on these areas, or in IISc I can find. Okay, so you will get more exposure than IITs or than in India to go out, explore yourself. You will get more expertise contacts. Okay, so what I say is better go for the top institutes, do full time. You will have a lot of growth in the career, a lot of exposure.
Thank you for sharing.
Thank you, sir. So participants, if you have any questions, I am just asking, you can just come up.
Dear participants,
Or if
please
you have
unmute
any
yourself,
suggestions to
ask any
me,
questions. Thank you, Pramod.
okay,
I don't
sir.
think there will be any questions from the participants. If any
Okay.
questions from the participants, please put in the chat box. It's my great pleasure to invite you from Reva University as a speaker for our session. This is online ATAL FDP sponsored by AICT. It is a 5 days program. Thank you for your valuable time sharing with us and sharing all his research experience in University of Science Malaysia with respect to CAD/CAM and artificial intelligence. And thank you very much, Pramod sir. On behalf of Principal Rajarashri College of Engineering and the coordinator of our online academy sponsored by SCT, I would like to thank you. Thank you once again.
Thank you, sir. Thank you very much. I would like to heartily thank Dr. Satish sir, Dr. Karthikeyan sir, and all the members who are involved in FDPs, ATAL FDPs. Thank you for inviting me. I'm overwhelmed for this invitation. Thank you very much. So, hope we will be in touch for our future interactions. And also thanks to the participants. Hope I could able to put some overview on the current trend. I hope I could able to understand and I could able to communicate well. I hope so. Thank you all.
Thank you. Namaste.
Namaste. Thank you.
Now, dear participants, we are closing the session 1 of the 4th day. So we'll be back for the session 2 at 11 a.m. sharply. So it is on Industry 4.0 through Asset Manufacturing by Dr. B.M. Tilak, Associate Professor from MIT Coimbatore. He is going to deliver a lecture. So please join us sharply at 11:15 a.m. Now we'll take 15 minutes break. So let us join us 11:15 a.m. sharply. Thank you all.